My name is Harriet Shapiro, and my project is on the effect of urban heat island mitigation strategy on surface and atmospheric temperature. Urban heat islands, or UHIs, refer to cities or other urban areas that are consistently warmer than their rural counterparts. This occurs because man-made surfaces trap and re-emit more of the sun's heat than the natural surfaces they replace. UHIs can be measured in two main ways: surface heat islands, which compare surface temperatures of cities to rural areas, and atmospheric heat islands, which compare air temperatures. Surface heat islands tend to be more extreme, while the effects of atmospheric heat islands have a greater impact. In fact, cities tend to be 0.5 to 4 degrees warmer than nearby rural areas during the day and 1 to 2.5 degrees warmer at night. This seemingly small increase in temperature has significant implications. To begin, UHIs contribute to global warming, particularly as cities expand to accommodate growing populations. Additionally, they increase heat waves and heat-related deaths, which are already the #1 cause of weather-related death in the US. Finally, by one estimate, the total economic cost of climate change could be 2.6 times higher when UHIs are considered than when not. The combination of these factors make it clear that UHIs are a very real problem our cities and world face, which is why I chose this topic. I believe that understanding how best to combat UHIs is a key component of fighting climate change as a whole. Luckily, there are several measures that can be taken to mitigate UHIs. Four commonly used mitigation strategies are green roofs, cool pavements, and trees. Green roofs are a layer of vegetation planted over a flat or minimally sloped roof. They combat UHIs by providing physical shade and through evapotranspiration. Similarly, tree canopies, which are represented by moss suspended over the simulations in this experiment, combat UHIs in a similar way. Cool roofs and cool pavements are those made with high albedo materials that combat UHIs by reflecting heat. The purpose of this experiment was to determine which of these four mitigation strategies is most effective in reducing UHIs. The independent variable was the mitigation strategy, with the control being no mitigation measure and the experimental groups being green roofs, cool pavements, and trees. The dependent variables were the increases in air and surface temperatures. The null hypothesis was that mitigation strategy would have no effect on temperature. The alternate hypothesis was that cool roofs will be most effective in preventing heat gain due to their high solar reflectance and greater surface area. To conduct the experiment, models were constructed out of plywood to represent 4 city blocks and the intersection between them. The roofs and base were painted black as the control, and the mitigation strategy could be applied one at a time. The temperatures in the air above the simulation and at the surface of the base and the roofs were measured. A heat lamp was then turned on for 1 hour, after which the temperatures in the same 3 spots were measured again. The increases in temperature for each of the mitigation strategies were calculated, averaged, and organized into a bar graph with error bars representing the standard deviations. The results showed that the control had the highest mean at each of the 3 spots. Meanwhile, the cool roofs had the lowest mean for the roof temperature and air temperature, and the trees had the lowest mean for the ground temperature. ANOVA tests yielded p-values of 0.05, suggesting the data was statistically significant in allowing the null hypothesis, which stated that mitigation strategy would have no effect on temperature, to be rejected. Additional t-tests were run to further understand the significance of the data, which showed that all differences were statistically significant except for between groups with very similar means. For example, the difference between the increase in air temperature for the green and cool roofs was not statistically significant because the means were only 0.1 degrees different. The results showed that the cool roofs were the most effective in preventing heat gain, which supports the hypothesis. However, there is no statistical significance between the cool roofs and green roofs. Furthermore, all 4 mitigation strategies were more effective than the control. The reason for the greater cooling capabilities of the roofs in this experiment may have to do with the surface areas. The roofs comprised 56% of the total surface area of the simulation, while the cool pavements and trees comprised 44%. As a result, their superior performance could have simply been due to their greater abundance. However, the ratio of ground to roof used was very purposeful, as an analysis of geographically diverse cities found that pavement covers approximately 30 to 45% of land in cities. Another reason the roofs may have done better is that they were located to the heat source and the point at which the atmospheric temperature was measured. For the ground temperature, the green and cool roofs were less effective, which makes sense because they did not directly affect the ground. Meanwhile, the tree canopies were most effective, followed by the cool pavements. The difference in performance between the tree canopies and cool pavements may have to do with the way they work to combat UHIs. Cool pavements combat UHIs by reflecting heat, while trees provide physical shade, preventing as much heat from reaching the pavement in the first place. The results of this experiment suggest that the physical shade provided by trees is more effective at cooling a surface than the solar reflectance provided by cool pavements. A similar but opposite pattern was observed for the roof temperature. The green and cool roofs were much more effective, while the cool pavements and trees yielded no significant difference compared to the control, because they did not directly affect the roofs. These results are conducive with other studies, as both cool and green roofs have been shown to decrease roof temperatures by anywhere from 28 to 40 degrees. While the data collected is insightful, it is important to understand its limitations. To begin, the moss, which was suspended between the buildings over the simulations, may not be an accurate representation of tree canopies in a real city. The moss may have provided denser coverage and more shade than actual trees, which could have skewed the results. Additionally, the entire experiment was conducted on a very small scale, and it is hard to predict how closely the results translate to a real city. In the future, this could be addressed by using larger simulations or by comparing these strategies in real cities where they've already been implemented. Another future study that could be useful is to examine the effectiveness of these mitigation strategies outside the context of a city. Every city is geographically unique, and it is unrealistic to assume, for example, that pavements make up exactly 44% of land in all cities. Given this, an experiment that tests these strategies in a way that eliminates all geographical variables could yield results that are more easily applicable to a variety of cities. In conclusion, this experiment supports the effectiveness of all four mitigation strategies examined in reducing UHIs. Furthermore, it suggests that green and cool roofs are most effective in decreasing urban temperatures. However, it is important to consider that this conclusion may be related to the layout of the model cities used and not applicable to every city. Either way, this experiment provides important insight into how best to combat UHIs. UHIs are becoming increasingly relevant as global warming and heat waves increase and intensify. Given this, it is vital to continue to research and compare mitigation measures, as was done in this experiment. Thank you for listening.